It is now my pleasure to introduce our second keynote speaker, Professor Volker Sorge. I hope I got it right, from the University of Birmingham, UK. Volker has been instrumental in reshaping the landscape of web technology standards development, influencing the conventional approaches employed by STEM publishers, and aiding accessibility support professionals in serving visually impaired readers. His efforts have resulted in the adoption of practical, open-source software technology for rendering mathematics in an accessible manner, enabling auditory and tactile transcription of mathematical formulas for widespread use. One of the biggest challenges is STEM education for people with visual impairments, and I look forward to hearing him speak about the challenges so that STEM education becomes more accessible and we have more inventors and co-creators and technologists who are visually impaired people, in case this was the barrier for them to participate in the co-creation. Welcome, Volker.
Thank you very much. Thank you for the kind introductions, and thank you very much for the fantastic pronunciation of my name. So my name is Volker Sorge, indeed. Right. So the first thing is I would like to point out that unlike any other speaker probably, I'm not using PowerPoints, I'm eating my own dog food, I'm talking about web accessibility, so everything I'll do is on the web, and you can read along if you like. I'll show you the URL. For those of you who can read along or play along, this URL is speechruleengine.org/talks/empower23. So if you have your screen reader, you can read along, and you can play along with the examples I have on the slides. And I'm hoping I'm not going to interfere too much because I have to move back and forth with our sign language interpreter. Right, so my name is Volker Sorge. I'm a professor at the University of Birmingham for document analysis and accessibility, but I also have an adjunct position at the IIT in Delhi. I'm a member of the MathChecks Consortium, where we do kind of mathematics for the web with two people. It's David Savone, who kind of does the visual side of things. I do the accessible side of things. And that's not all. I've got a few more affiliations. I have an own company which is called Progressive Accessibility Solutions, where we commercialize STEM diagram solutions, accessible STEM diagram solutions. I work for CTO for a company which is called Equivalent Design, where we currently build the next generation of SVGs for the web, which are reactive to all kinds of accessibility needs. And I work as a CTO for Helix Opportunity, where we build UX research solutions. And I'm very happy that Neha Javad is here, who is our program manager there. Right, so let me get finally into the talk. What am I going to talk about? I'd like to motivate that we can do STEM accessibility on the web. We can do it now, we can do it today. And we can do all the hard parts there are. And this is what I'm trying to motivate today. I'll show you some examples, and I will eventually lead up to the holy grail of how do we produce STEM content. STEM, just for those of you who are not familiar with the acronym, scientific, technology, engineering, and mathematical content from scratch, so it'll be accessible out of the box without any remediation, without any hassle, without any fuffing around and fuffing about. So first of all, it's always good to remind people, why is scientific content difficult? What are the problems with scientific content? Why is it hard to make accessible? Well, the easiest to convey reason is that all the hard ALF and Y problems, all the hard accessibility problems are found in STEM subjects. So you have all kinds of things. You have not only do you have things like tables, formulas, you have diagrams, but you also have very specialized vernacular, which you might not find in a dictionary, which tells you how to read it out. You have scripts, different scripts. You sometimes have different characters or from different alphabets within the same word. So you have a protein name, for instance, where you have a kind of Greek letters interspersed with Latin words, and so on and so forth. And the next thing is that you cannot just capture it by just a lookup table. STEM, by their very nature, scientific languages are infinite. We're constantly coming up with new concepts, constantly we're creating new vernacular. We need effectively a way how to capture that without having to kind of enlarge lookup tables on a daily basis. So that's why the traditional approaches to STEM fail. And the traditional approaches to STEM historically, which actually work quite well for education, fail as well because of technology today. Right? So in the olden days, how would a scientific textbook, a math book for your blind student, for instance, made accessible? Well, you have somebody, maybe you read it out. Sit down an expert, read it out, explain the diagrams, explain the figures. Have somebody set it into Braille so you can emboss it, you can give it to your student, they can read it. These days, what's happening? Well, nobody's using textbooks anymore. We all move to online material. I create my lecture material the night before I give the lecture. There is no time anymore for some person in an accessibility office to actually do the remedial steps and provide a version for the blind student, for the person who needs big magnification, and so on and so forth. So the material in many ways is ephemeral, so we need solutions that work now, here, there, and then, and ideally automatically. And that's what I'm trying to build. So that's the aim of my work. Put together, use the richness of the web, all the standards that are already out there, the HTML, the CSS, the scalable vector graphics, the ARIA that exists in order to make STEM accessible. And thereby, and would like to emphasize what my aim is not. That's always important. I do not want to impede the authors by telling them, oh, you only can author your math in this particular syntax. I do not want to force readers to just use a particular system. Oh, this only works on Windows with this screen reader and this special library. No, ideally, it should work everywhere for everybody, no matter what their needs are and no matter what their normal assistive technology environment is. And the way I like to do this is by using the power of the web, which has effectively all the things that are there for the visual display of content. And in the background, you can hide a lot of information, which will then allow you to put in meaning that can then be exploited in order to make it accessible in different ways. And I'll start you out with a bit of an example from mathematics. And mathematics, so that's a formula that is typeset with math checks. I'm not quite sure what browser I'm using. I think it's a Chrome. And the mathematics in there is not given as some sort of HTML. The mathematics in there is given as LaTeX. And it's being translated into something that can actually be viewed. And now we can also make this thing accessible.
X equals start fraction negative b plus or minus start root b squared minus 4 a c end root over 2 a end fraction.
So for those of you who are familiar a bit, this was the quadratic formula, of course. That's I think the Germans call it the midnight formula. For some of you, so the interesting thing is that the screens are slightly different here. For those who can actually see the slides, on the left-hand side, you can see the highlighting much better. There's a subtitle which actually tells you what it read out, and there was highlighting going on while it was reading out. I would also like to point out none of this uses a screen reader. If you have a screen reader switched on, it would use the screen reader. Right now, all of this is just using the Web Accessibility API, and it just reads out that formula. And how does this actually work? How do we make this happen that it works like this and that the formula is being read out so nicely? Well, the thing is, as I said, the library that's rendering the mathematics is called MathChecks. In the background, there sits another library, which is called the Speech Rule Engine. What it does is, it does a semantic interpretation of the mathematical formula and then translates it into speech. And it then injects this information kind of think about it as a perpendicular view or a different view on the formula that you have in the page, which allows it then to be read out and be read out in a mathematical fashion. And the speech rule engine is not just in MathChecks, it's originated. I was spending a sabbatical year at Google in 2012-13, where I started implementing the system within ChromeVox. These days it has taken on a life of its own. It's being used by a number of systems. Equatio, some of you might be familiar with TextHelp's Equatio, it's big in there. There's in some other, quite a number of other systems use it. Publishers use it to produce alternative text and so on. And what the system really does is it takes the mathematical syntax, which is either, for instance, in LaTeX, as is normally the case in most web pages, or in MathML or in ASCII Math. ASCII Math is a more simplified version of LaTeX. And then it tries to understand what that actually means mathematically. It translates it into an abstract syntax tree which represents the mathematics and then turns this into speech. And I've put together, for those of you who can see the slides, I've put together this is not even the quadratic equation, this is just the quadratic formula, and the quadratic formula, this is the quadratic equation, sorry, the other way around. It's just ax squared plus bx plus c equals 0. Once in LaTeX where it's easy to read, and once in the horrible MathML format where it's really, really overblown and complex. But what the main point I'm trying to get across here is that this is very linear. There's hardly any distinction between the symbols, right? It's just a bunch of symbols. The only thing where you get a slight difference where you notice that there's something going on two-dimensionally is that you have a superscript, which is either the caret 2 or the m sub in MathML. And what the speech rule engine does is it kind of parses this input, and then here's a visualization what it does internally in terms of rewriting that formula. So it takes it, it disassembles it and reconstructs it from the ground up, giving it a mathematical interpretation. And what you see here is a tree which kind of puts this ax squared plus bx plus c equals 0 into equational notation where you have at the root of the tree, you have the equation, then you have the right-hand side, which is 0. Left-hand side, you have the sum, and the sum has 3 children, which are the 3 summands, the ax squared plus bx plus c. Right? And once you have that interpretation, what you can then do is you can then use that interpretation. Let's
A x squared plus.
So this is the auto voicing, but what you can now actually do is you can use this tree I've showed you in order to navigate in a mathematically meaningful manner this equation. So we dive into that equation. We first go on the left-hand side.
A x squared plus b x plus c.
It's usually a bit fast on my machine, but I don't know why this Chrome is particularly slow. Anyway, and then you can walk through the equation.
Equals 0
Right?
equals a x squared.
You can also dive into the equation.
A x squared
And now I'm in the summand, and I go to the
plus
and I go to the next
b
summand, and so
x.
on, right? And all this is predicated on the fact that we now have effectively a semantic valuable or valid interpretation of the formula. And this is nice. So what we can do now is we can effectively read math to students, and the students can use that, right? Like they can understand what's on the page. But math is not just about listening to formulas or reading formulas, it's also about using them, right? So you would also like to give the people the possibility to actually do their own input, right? Do their own mathematics. And that's one thing you can do as well, of course, and I'm going to show you a little example. This is just on the math text page. Here is our usual live demo. And say we start a new mathematical environment. If you're not familiar with what I'm doing now, is I'm going to put in the LaTeX parts. So this is just a display formula I'm starting, and let's say I'm going to start, I don't know, ax squared, for instance. Here you go, there it is, plus b plus c equals, I don't know. Let's start with something which initially will be wrong, a fraction, right? So you can, for those of you who can't see it, it now tells us, well, there's a missing argument for our fraction, and then it gives us effectively an error which would be read out by the screen reader. And let's give it now, right? We need a second argument for it, and eventually it's there. So the nice thing is you can use all of this technology. Now we could read it out again. I'm not going to do this now because I would have to really switch on a screen reader for this at the moment. You can use all of this technology, not just to get students to read the math that you give them, but also to input their own math and work with their own math and actually allow this to do. And one of the main and important parts of this is we give them a means to input the mathematics, which is normally in line with what, for instance, their professors would do. You know? It's LaTeX you input. This is kind of the most commonly used mathematical markup. They don't have to jump through hoops, going through WYSIWYG editors. They don't have to use something outlandish like MathML. They don't have to learn extra steps in order to get into Word's equation editor and jump around. That's already hard enough for mathematical experts which can see the system, and it's even harder for students that cannot. Right. Another thing, of course, that I would like to be
Modifying above. Niblack. With right.
I'm not going to read that out now. So here's a slightly more complex formula. It's a curl of a vector field. It's a physics formula. And the way we can make it accessible, because we have all that semantics in the background now, is not just with speech, but also tactily. If you can see the screen, there is now a Braille line underneath the entire formula. That is the Braille that would show up on your Braille display. And again, you can do the same. Do the same navigation.
Modify.
And you can navigate into the single elements, and thereby, because your Braille display will not be able to display a formula quite that long, but you can now kind of break it down into the parts that you can actually read. Most people have maybe 20 block Braille display with them, but if you have 80, then you can have all 80 formulas, all 80 characters, and so on.
Equals.
Again,
Left parenthesis.
Entire formula as much as you like. And the Braille you can see here it's Nemeth, which is commonly used in the United States. It's a particular elaborate dialect of Braille, which allows you to really, really express a lot of mathematics, fonts, all kinds of different symbols. Now we can do other things as well, and I'm particularly happy to show that to you because I think this is an important part. So I've been working with people in Germany. So in Germany and some other European countries, Slovenia is another one, they're going a different direction with the Braille over the last 20 years or so. So in many places, you would teach children a particular dialect of Braille in order for them to be able to do mathematics. So for instance, in the US, it's Nemeth, and I know that in the UK, used to be some Braille dialect, which now, I think, superseded by UEB. In some other European countries, notably Germany, Slovenia, I think somewhere in the Czech Republic as well, they've gone a different route. For the last 20 plus years, they've been teaching children LaTeX since effectively grade 1. And they've been in, of course, you don't really need to teach much LaTeX. That comes in maybe once you start with exponents and indices and so on, and then fractions. But they're teaching them LaTeX. And then that allows a couple of things. Number one is it allows them to express it directly as a one-to-one correspondence on their Braille display. And I'll render the LaTeX here. And I'm not going to read it out, but the Braille you can see here is 8-dot Braille. What does that have as an advantage? Well, you do not need any particular indicator. So when you have a normal Braille, you have kind of shift indicator saying, oh, the next character is a capital letter. The next character is actually a number. In 8-dot Brailles, you don't have to do that anymore, right? As computer scientists, of course, we know 8 bits are always enough to express pretty much everything we want to express, right? And that's the same principle here, going from 6 bits to 8 bits. Right? And what they then do is they then translate the LaTeX directly into 8-bit Braille. And again, let me do that for you here. Again, that then comes out on your Braille display effectively as your LaTeX code, which is easy to do if you have LaTeX in the page already. This is a work I've been doing with some Germans, therefore everything else, the text was actually in German. What's scientifically the hard part or the interesting bit from my point of view was that we now implemented an algorithm which allows you to also get all the sub-expressions as meaningful LaTeX output, which sounds trivial, but if you know that LaTeX or TeX in general is a Turing-complete language, it's not that trivial, so it's being passed with a recursive stack machine or stack automaton, which is not a trivial example then, or trivial feat to get all the intermediate steps out and into some passable LaTeX. Anyway, so we've done that. It's out there now, and we're starting to test with people in somewhere in Baden-Württemberg, which in a German state in the southwest. Right. And of course, we can make a lot of complex mathematical material. Here's a big logic proof. We can make all this accessible as well. In the interest of time, I don't want to go into those details, just to let you know that, yes.
Inference rule. Label.
So this is an inference rule, and it's a ginormous inference rule. It's practically a diagram. It's practically a graphic which we have on the page, which obviously brings me to my next subject. Not math. STEM doesn't only consist of formulas, but it also consists of diagrams. What do we do with diagrams? Well, we do the same thing effectively. We take the diagram, we recognize what it is, we then enrich it semantically, and we use the semantics in order to make it accessible with a screen reader. And I'll give you an example which we're currently commercializing with in my company. And that's a chemical diagram. And let's just have this talk to you.
Molecule consisting of ring with 6 elements and functional group COCOCH3 and functional group COOH. Aspirin.
It's actually aspirin, right? So at first it told you what the entire molecule was, and then you can actually also get a name for it, right? And what this is in here, that's an SVG. I'll show you briefly why this is indeed an SVG. We can change the color, we can blow it up, we can do all kinds of nice little things with it. And then we can also, a bit similar to what we just had in the math.
Benzene ring substitutions at positions 1 and 2.
What happens is the benzene ring is now being focused, it's being zoomed in, and it's being read out. And of course, if you have no idea what a benzene ring is, we can switch off.
Ring with 6 elements, double bond between positions 4 and 5, double bond between positions 2 and 3, double bond between positions 1 and 6, substitutions at positions 1 and 2.
Right, so this is what a benzene ring is. Not very exciting.
Benzene ring substitutions at positions 1 and 2.
I'm not a chemist, but this is what they like to hear. And where does it all come from? Well, our math came from LaTeX input. Our chemistry actually comes from diagrams. It actually comes from diagrams that are normally given as JPEGs, as GIFs, as PNGs, or it could potentially come from a chemical identifier. And what happens is that we do the interpretation of the image, we kind of recognize the image, we then interpret what these parts of the image actually mean chemically, and then we use this in order to put together a navigation model plus all the speech, and all of this happens automatically. And there's nothing in the system which is more than kind of an overview how you would view a formula. So for instance, we've just had aspirin. Aspirin consists of a couple of elements, and this is what the system does, right? So it recognizes all these elements, right? And the elements are recognized as a bunch of lines and a bunch of characters. That's all there is, right? And then it tries to reassemble this bag of geometrical primitives. So first of all, it kind of figures out where are the bonds and how are they being connected. What is a double bond? What is a connecting line? Connecting corners here, for instance, are normally carbon atoms, and so on. And then it tries to figure out the major building components of the molecule, and that's normally, there's three parts of it. There's either big chains, right? Chains of carbon elements. There's rings, like this one here, and then everything else that's just left over is called functional groups. And that's pretty much all it does. And then it goes away and asks databases out there on the web, and there's a bunch of those. There's one, for instance, by the Royal Chemistry Society, and I think it's called ChemSpider. There's others from the National Institute of Health, where you can just send partial chemical specification, and they come back with a name, for instance. So we don't have any names in the system, whatever, the aspirin, the benzene ring, none of this. The ester, the carboxylic acid, none of them is anywhere in the system. It's kind of named automatically, so we can make use of every new chemical information that comes in, and these databases grow on a daily basis. And they're particularly useful then when you try to understand slightly more complex elements. So for instance, here we have an element which comes out of a US patent application from the year 2010, I believe. And the recognition algorithm kind of goes into that patent application, finds the chemical formula, and then it makes it accessible. And
Serame sign.
Naming it, and then it gives it also, let me put this, and then what it does is it gives it an ordering of how you navigate this chemical formula. How do you walk through this molecule? And all this, there's rules for that. Chemists have rules for everything, luckily, and all we had to do is kind of figure out what these rules are, and then we can walk through them.
Fused ring system phthalate with 2 subrings. Substitution at position 2.
What chemists like in particular are big ring systems, so that's where you start, and then from there you can start outwards and walk through your system further and further and further. All right, so we walk over.
Piperidine ring. Substitutions at positions 1 and 4.
And again, all these chemical names, we have no idea what those are. They come out of these databases. Right. So this is chemistry. And chemistry is nice, because chemistry, they've got a lot of rules, and in many ways, although those diagrams look fairly complex, they are actually quite nice to understand, because you can identify the chemical compounds quite easily, and they are nicely put together according to the organization is called IUPAC. They put together all these rules, and all you have to do is follow these rules and implement those. Now, there's plenty of other diagrams, of course, out there, which we also would like to understand, and which we also would like to make accessible. And they are not quite that simple to understand. In particular, of course, being in mathematics, mathematics is one of those elements where I've put together a couple of examples on the slide. So we can do flowcharts, we can do data visualizations, but what about general mathematical formulas? And that's work I've just been doing recently with a chap from Michigan called David Austin. And there the basic aims are that, okay, if we have a mathematical diagram, we might be able to make it accessible. Is there a way to also give people the opportunity, if they can't see the diagram that they're building, to actually build diagrams easily and know, first of all, what they mean and that they're accessible? So what we've done for this is we start putting together diagramming languages for visually impaired authors, which then allow that diagram to be built in a particular dialect of LaTeX, which is called TIXI, and then it's being generated, and it's being generated accessibly. And here's just an example of that language, not particularly exciting. It's a very small XML language which effectively specifies things like the grid axis if you need any. It specifies things like functions that you want to have plotted, and it specifies other points of interest that you might be interested in. And then it's being built and annotated. And I'll show you a couple of examples, because examples are normally more exciting than actually looking at XML dialects.
8 equally spaced points on the circle, 45 degrees apart, starting at 1 on the x-axis.
So what is this? This is the unit circle, right? So it tells us what the components
8 equally spaced points on the circle, 45 degrees apart, starting at 1 on the x-axis. A pair of perpendicular axes for Cartesian coordinates.
So all of this speech is automatically generated out of the specification I showed you earlier.
A circle of radius 1, centered at the origin.
And again, you can navigate this diagram as you wish. You can write it yourself. You can, if you're visually impaired, you can then inspect it on the screen, and then you can do all kinds of other output with it, which I'll show you later, which you can effectively put it into tactile output. And how do we bring all this together? Because the ultimate goal is, at least for scientists like me, but also for other authors, for teachers and so on, to be able to just write a document in their preferred style, ideally, and then generate it so it's visible. So visually, it is what you expect, what you can publish, what you can give your students that are fully sighted, but then where you can generate other alternative media directly out of it, which you can give to your visually impaired students, which you can give to your student who likes tactile graphics, give to your student who wants to read it in Braille. So we bring this all together in a language called pretext. What is pretext? Yet another language, right? Actually, it isn't. What pretext is a fairly uncomplicated XML vocabulary that tries to bring together the good parts of LaTeX, and the good parts of LaTeX are the mathematics, none of the rest, together with structure, which you normally have in XML documents. Well, and from this kind of fairly basic format, you can integrate formulas, you can integrate diagrams, and you can integrate code, which is particularly interesting for computer scientists. And now you will tell me, of course, oh, well, but don't you want it so nobody has to change their authoring style, nobody has to change the way they work. Well, no, nobody really has to change the way they work. What you can do is you can effectively translate pretty much anything that's out there into pretext, from which you can then generate all these other formats. And there's a, for instance, if you're familiar with Pandoc, there's a processor for Pandoc, which allows you to get your Word into that format, which allows you to get your standard LaTeX document into the format, Markdown, what have you. And then once it's in that format, then you can actually start building. You can do it for print. You can start building a PDF, of course, you know, like you would do out of a LaTeX document or out of your Word document. You can get it on the web. You can make EPUBs out of it. You can make Jupyter notebooks out of it. And all of these contain the accessible components. They contain the mathematics, which can be made accessible with math checks. So it's being rendered with math checks, so you can run your screen reader on it. You can use math checks as an accessibility tool. You can use it for the diagrams. The diagram I showed you earlier, that is being generated directly with code that is in pretext, and then you can exploit that. And then you can exploit that in order to make all kinds of other elements out of it. And one in particular, that's tactile mathematics that we can do. That's a work we're currently doing with the American Institute of Mathematics and the National Federation of the Blind, where you generate textbooks, translate the textbooks into pretext, and then generate them in tactile format directly. Normally that costs, from what I understand, about $50,000. For a single textbook, it takes about 6 months. We can do this in about a couple of hours. It's not perfect yet, but it's a start. Here's an idea of how one of those tactile diagrams actually looks like. That's from an abstract algebra book, and can be generated out of the box from this format. And finally, to really get into the holy grail, here's a research paper that David Austin and I wrote for one of the conferences where we actually published about that stuff. And just to show you that we're really eating our own dog food, that research paper contains graphics, of course, because you want to show off. These are the kind of graphics that we can deal with. Then you give it to one of those publishers. It's a 3-letter word publisher. So I'm not going to tell you that. What they do is they get all these in BNGs. They want all text for it. And then what else is in there is effectively absolutely inaccessible. Whereas when we put it on the web, if it works, it doesn't, of course, then it doesn't work. Well, there you go. That's the if. Why does it not work? Anyways. Right, the last thing I want to show you there is that it the diagrams now didn't work for some reason. Sorry about that. They normally do. The final thing I want to show you is that what else is in there? There's code. Here's a bit of XML code. The code I showed you earlier, that's accessible as well. For those of you who can see how I navigate that now just with a keyboard, and that is what would be spoken. There's ARIA labels in the background with a screen reader. That's not auto-voiced, but you can dive into these elements and you can walk around and look at the code. And just to finish it off, once we gave this paper to the publisher, of course, all of these environments all of a sudden were pictures only, absolutely inaccessible. And that's exactly what we want to avoid. Right, I'm mindful of the time. I thank you very much for your attention. All I would like to finish off with is that to reiterate my belief, all the basic mechanisms for making STEM accessible on the web are already there. What we need to do is we need to actually use them, and we need to use them right. And in particular, we must not drink the Kool-Aid of thinking about, oh, once everything is in a particular standard, and once everything is in here, then it will be automatically accessible. That is not right. It doesn't matter how you author, what you author, and in what normal environment you author it in. As long as you translate it right, and as long as you as long as you do not throw away any of the sources, we can make it accessible. Right? Once something is in an image, it's lost. As long as we have all the content, all the LaTeX, all the chemical markup, one can do something with it. And if we can't do it just yet now, maybe in a year's time, there will be the technology there. So my take-home message for you, all of you is, when you do your accessibility remediation, please make sure that you're future-proof. Do not throw away your sources. Do not move away from a lingua franca for mathematics into one that only browsers can read, and so on and so forth. Thank you very much.